The night sky is a tapestry of twinkling lights, each a distant sun in the vast expanse of the universe. These stars, the building blocks of galaxies, are not all created equal. They come in a dazzling array of sizes, from diminutive dwarfs to colossal giants that dwarf our own sun. Understanding the different sizes of stars is key to unraveling the mysteries of their birth, evolution, and eventual demise. Imagine a world where the stars are like grains of sand on a vast cosmic beach. Some are just specks, barely visible to the naked eye. Others are like pebbles, their faint glow hinting at their immense distance. And then there are the giants, boulders of burning gas that illuminate the cosmos with their brilliance. The smallest stars are like fireflies flickering faintly in the darkness. The largest are like celestial beacons, visible from across the universe. The sheer range of stellar sizes is a testament to the incredible diversity of the cosmos. Our journey through the universe of stars begins with the smallest, the cosmic dwarfs, and progresses to the largest, the hypergiants, whose sheer scale is almost beyond comprehension. At the lower end of the stellar size spectrum, we find the brown dwarfs. These enigmatic objects are often referred to as failed stars because they lack the mass to ignite the nuclear fusion that powers true stars. Brown dwarfs are typically larger than Jupiter, the largest planet in our solar system, but smaller than the smallest red dwarf stars. Red dwarfs are the most common type of star in the Milky Way galaxy. These cool, faint stars may be small, but they are incredibly long-lived. A red dwarf can burn for trillions of years, far longer than the current age of the universe. Barnard's star, a nearby red dwarf, is a prime example of these long-lived stellar denizens. Think of a brown dwarf as a candle flame that never quite catches. It has the potential to burn, but it lacks the fuel to sustain a true fire. Red dwarfs, on the other hand, are like embers in a fireplace, glowing faintly but steadily for eons. The difference in size between a brown dwarf and a red dwarf is relatively small, but it has profound implications for their lifespans. Brown dwarfs will slowly cool and fade away over billions of years, while red dwarfs will continue to shine for trillions. Our own sun is a yellow dwarf star, a relatively common type of star in the Milky Way. It is a main sequence star, which means that it is fusing hydrogen into helium in its core. The sun is about halfway through its main sequence lifespan, which is estimated to be around 10 billion years. While our sun may seem unique to us, it is just one among billions of similar stars in our galaxy. Other main sequence stars, like Sirius and Beta Centauri, are larger and hotter than the sun. These stars burn brighter and live shorter lives. Imagine the sun as a light bulb. It provides a steady source of light and heat, but it will eventually burn out. Larger main sequence stars are like spotlights, shining more intensely but for a shorter period. The size of a main sequence star determines its temperature, luminosity, and lifespan. Larger stars burn hotter and brighter, but they also consume their fuel more quickly. Section 4. Stellar giants, blue and red. As stars age, they evolve and change. When a star like our sun exhausts the hydrogen fuel in its core, it expands and cools, becoming a red giant. Red giants are much larger and cooler than their main sequence counterparts. Our sun will eventually become a red giant, engulfing the inner planets including Earth. At the other end of the stellar size spectrum are the blue giants. These massive hot stars are relatively rare but incredibly luminous. They are often found in regions of active star formation where they illuminate their surroundings with their intense blue-white light. R136A1, one of the most massive stars known, is a blue hypergiant with a mass over 300 times that of the Sun. Imagine a red giant as a balloon being inflated. It grows larger and larger, but its surface cools as it expands. Blue giants are like giant arc lamps, blazing with incredible intensity but burning out quickly. The difference in size between a red giant and a blue giant is staggering. A red giant can be hundreds of times larger than the Sun, while a blue giant can be tens of times larger still. Section 5. Hypergiants, Titans of the Cosmos. The largest stars in the universe are the hypergiants. These colossal stars are incredibly rare and short-lived. They are so large that if one were placed at the center of our solar system, its outer layers would extend beyond the orbit of Jupiter. Hypergiants are constantly shedding their outer layers in powerful stellar winds, creating vast nebulae of gas and dust. Stephenson 2, 18, the largest known star, is a red hypergiant with a radius over 2,000 times that of the Sun. VY Canis Majoris, another famous hypergiant, is slightly smaller but still dwarfs our Sun in comparison. Hypergiants are like cosmic fireworks, burning brightly but briefly. Their immense size and luminosity make them some of the most awe-inspiring objects in the universe. Imagine trying to stack Earths on top of each other to reach the surface of a hypergiant. You would need millions upon millions of Earths to reach the surface of one of these stellar titans. The sheer scale of hypergiants is difficult to comprehend. They are so large that they challenge our understanding of the laws of physics. Section 6. The life and death of stars. The size of a star is the most important factor in determining its lifespan and ultimate fate. Small stars, like red dwarfs, live long, slow lives, gradually fading away over trillions of years. Massive stars, like blue giants and hypergiants, live fast and die young, exploding as supernovae that seed the universe with heavy elements. Our own sun will eventually exhaust its nuclear fuel and become a white dwarf, a small dense remnant of a star. White dwarfs are about the size of Earth but contain a mass comparable to that of the sun. They are incredibly faint and will slowly cool over billions of years. The life cycle of a star is a delicate balance between gravity and nuclear fusion. Gravity pulls the star's material inwards, while nuclear fusion pushes it outwards. The size of the star determines which force will ultimately win. Imagine a star as a seesaw. Gravity sits on one side, while nuclear fusion sits on the other. The size of the star determines which side of the seesaw will go down. Understanding the life and death of stars allows us to trace the history of our galaxy and the origins of the elements that make up our planet and ourselves. Section 7. Unlocking the universe's secrets. Studying star sizes is crucial for understanding of the universe. By observing and analyzing stars of different sizes, we can learn about their properties, evolution, and the processes that drive the formation and evolution of galaxies. The study of star sizes is not just about satisfying our curiosity about the cosmos, it has practical applications as well. For example, understanding the life cycles of stars helps us to predict the future of our own sun and its impact on Earth. Imagine the universe as a giant puzzle. Each star is a piece of the puzzle, and by studying its size and other properties, we can start to put the puzzle together and understand the bigger picture. The universe is full of wonders, and the study of star sizes is just one of the many ways that we can explore and learn about our cosmic backyard. To delve deeper into the wonders of the universe, I highly recommend exploring resources like the Universe in a Nutshell app. It offers a fantastic way to visualize and understand the vast scales and phenomena of the cosmos.